Alright, let's tackle a problem involving Debye temperature and heat capacity. We are looking at a two-dimensional insulator that has a Debye temperature of 150 Kelvin. The question asks for the ratio of the heat needed to raise its temperature from 1 Kelvin to 2 Kelvin compared to the heat needed to raise it from 2 Kelvin to 3 Kelvin. Let's walk through the solution step by step. Step 1. Specific heat for a 2D insulator at low temperatures. First off, we need to know how the specific heat behaves for a two-dimensional insulator, especially at low temperatures. For these materials, when the temperature, let's call it T, is much lower than the Debye temperature, which we denote as theta sub D, the lattice specific heat is proportional to T squared. So we can write the formula for the specific heat P sub V as C sub V as C squared. So we can write the formula for the specific heat C sub V as C sub V as C sub the m times T squared, where A is just a constant. Before using that formula, we should check if the temperatures we're dealing with are actually low enough. The Debye temperature given in the problem is 150 Kelvin. The temperatures we care about are 1 Kelvin, 2 Kelvin and 3 Kelvin. Since 1 Kelvin is much less than 150 Kelvin, 2 Kelvin is much less than 103 Kelvin and 3 Kelvin is much less than 103 Kelvin, our low temperature approximation for the specific Kelvin, our low temperature approximation for the specific heat C sub V being proportional to T squared is specific heat C sub V being proportional to T squared is perfectly valid here. Now to find the heat required to raise the temperature of a substance from one temperature T1 to another temperature T2, we need to integrate the specific heat over that temperature range. So the heat Q is the integral from T1 to T2 of C sub V dt. Since we know C sub V equals A times T squared, we can substitute that into the integral. Q equals the integral from T1 to T2 of A times T squared dt. To evaluate this integral, we pull the constant A squared dt. To evaluate this integral, we pull the constant A out and the integral of T squared with respect to T is T cubed over 3. So Q equals A times T cubed over 3 evaluated from T1 to T2. Plugging in the limits, this gives us A over 3 times the quantity T2 cubed minus T1 cubed. Okay, let's use this formula to find the heat needed for the first temperature range from 1 Kelvin to 2 Kelvin. We call this Q1. Here T1 is 1 Kelvin and T2 is 2 Kelvin. So Q1 equals A over 3 times the quantity 2 cubed minus 1 cubed. 2 cubed is 8 and 1 cubed is 1. So Q1 is A over 3 times 8 minus 1, which simplifies to A over 3 times 7 or simply 7A over 3. Next, we calculate the heat required for the second range from 2 Kelvin to 3 Kelvin. Let's call this Q2. Using the same formula but with T1 equal to 2 Kelvin and T2 equal to 3 Kelvin, Q2 equals A over 3 times the quantity 3 cubed minus 2 cubed. 3 cubed is 27 and 2 cubed is 8. So Q2 is A over 3 times 27 minus 8, which simplifies to A over 3 times 1NE over 3. Finally, the problem asks for the ratio of the heat required from 1 Kelvin to 2 Kelvin. That's Q1. And the heat required from 2 Kelvin to 3 Kelvin, that's Q2. So we need to find Q1 divided by Q2. That's the fraction 7A over 3 divided by 19A over 3. Notice that the A over 3 terms appear in both the numerator and the denominator, so they cancel out nicely. We are left with 7 divided by 19. This means the ratio is 7 to 19. So the ratio of the heat required to raise the temperature from 1 Kelvin to 2 Kelvin and from 2 Kelvin to 3 Kelvin is indeed 7 to 19.